So we'll go ahead with the today's session. So once again, a very good afternoon to all of you. We are dealing with haloalkanes and haloarenes, right? We have completed till the chemical reactions of haloalkanes in the previous class. Okay, there were three reactions: nucleophilic substitution and electrophilic elimination reaction and reaction with metals. So these are the three reactions we have covered under the reactions of chemical reactions of haloalkanes. Okay. So today we are going to deal with the reactions of haloarenes, and at last we will discuss a small topic called polyhalogen compounds. Okay. So under this topic, the learning objectives for this session is nucleophilic substitution reaction. The second reaction is electrophilic substitution reaction. And the third one is reaction with metals. So these are the three reactions which we are going to learn under the reactions of haloarenes. And at last, we will discuss about the polyhalogen compounds and its uses and advantages and disadvantages. Okay. So I will start with the first chemical reaction, which is nucleophilic substitution reaction. Okay. So coming to the nucleophilic substitution, we have already studied the same reaction with haloalkanes. But there we did not have any difficulty, and there we have studied two types, SN1 and SN2, right? But here, coming to the reactions of haloarenes, the nucleophilic substitution has some, they are actually less reactive. Okay, I will discuss the reasons when in the next slide. So before that, here I would like to classify all the three reactions, and I would like to give you the name of the reaction which we are going to learn under each case. Okay. So talking about the nucleophilic substitution, here we will study about the replacement of halogen by OH group. Replacement of halogen by OH group. So the halogen nucleophile will be replaced by OH nucleophile. So those reactions we will see. And in the electrophilic substitution, we will study 5 reactions. The first one is called as halogenation. The second is called as nitration. Third is called as sulfonation. Fourth is Friedel-Crafts alkylation. And the fifth reaction is Friedel-Crafts acylation reaction. Okay. So these are the 5 types of reactions, very important reactions of haloarenes. Okay. Then the third is reaction with metals, right? So here we will study 2 reactions. One is Wurtz-Fittig and the other one is Fittig. Got it? So these are the reactions, the type of reactions which we will cover under each category. So now let me go one by one. Let me start with the nucleophilic substitution. So as I have said now, the haloarenes are extremely less reactive. The haloarenes are extremely less reactive towards the nucleophilic substitution. Okay, this is a very important statement. It is very less reactive towards the nucleophilic substitution because of 4 reasons. So we will study each and every reason one by one with the explanation. Okay. So the first reason is because of its resonance effect. To understand the resonance effect, I would like to take an example for haloarene. So let me take chlorobenzene. Chlorobenzene is a haloarene. So here, the lone pairs, there are 3 lone pairs on chlorine, right? So they will undergo the delocalization. The delocalization of pi electrons will happen here, and the electron will be shifted like this, and it will lead to one more structure. And in this structure, the negative charge will come here, and the pi electrons will come to the below carbon, and it will lead to the third structure. And from the third structure, if you delocalize the electrons like this, you will get a fourth structure. And from the fourth structure, again, if you bring the negative charge inside the ring, And if you take the pi electrons to the chlorine, you will get the fifth structure again. Okay. So these structures, in these these are the 5 resonance structures of this chlorobenzene. Okay. So in the middle 3 structures, if you see, the carbon and the chlorine, is taking the partial double bond character. Carbon chlorine possess the partial double bond character. So here in this here if you see in this CCl, it is single bond. But in all other cases, it is double bond. So if I draw the resonance hybrid of this molecule, since the pi electron is getting delocalized over the entire ring, I will draw the resonance hybrid like this. Resonance hybrid means all the delocalization of electrons will be shown in only in a single structure. Okay. So all of you can able to see the resonance hybrid, right? I think this doesn't go, looks good. I will draw here again. So here you see, this is the chlorine. And the pi electrons are getting delocalized over the 6 carbon and the chlorine. So here you see, carbon and chlorine is possessing or it is acquiring the partial double bond character. It is not a purely double bond, one single bond and one half kind of thing. So it is a partial double bond character. So in normal haloalkane, for example, if I take CH3Cl, here it is a purely single bond. The carbon-chlorine bond is a purely single bond. But here we are getting a partial double bond character. What will happen? The double bond will be more strong compared to the single bond. Okay, so it is difficult to break. Since this bond is very difficult to break, the chlorine cannot go out. Chlorine cannot go out. If it goes out, the other nucleophile can come and substitute, right? So this chlorine will not go out so easily. So the nucleophilic substitution is becoming very less reactive for haloarenes. Clear? Can you all able to understand this point? Shall I go for the second reason? Adarsh, Bishan, Madhukar and Janvi Roying, students, can you all able to understand this? Shall I go for the second reason? Yes. So please wait for some time. There is an issue. Can you all able to see the screen? Yeah. Okay, the second reason is the difference in hybridization. If I talk about the hybridization of both haloarene and haloalkane, in case of haloarene, the halogen is attached to the carbon, which is doubly bonded. Double bonded carbon means the hybridization of that carbon is sp2. Okay. But in case of haloalkane or CH2Cl, the chlorine is attached to the sp3 hybridized carbon. It is an sp3 hybridized carbon. So in sp2, the S character is more, right? So in sp2, the S character is more. So here 1:2 ratio only. So here S character will be around 33.3%. But here 1:3 ratio. So it will be 25% of S character and 75% of P character. So here 33.3 is for S. Remaining 66 point something will be for P. Okay. So if I compare these two, the S character is more in case of sp2. So since the S character is more, the electronegativity will be greater. Greater the S character, greater will be the electronegativity. Okay. So because of this reason, the carbon-chlorine bond length is 169 picometer. And here the carbon-chlorine bond length is 177 picometer. If the bond length is very less, then it is a strong bond. Okay, it is a bond length is very less, bond strength is more, right? If the bond strength is more, it is very difficult to break the bond. It is very difficult to break the shorter bond than the longer bond. Okay, so this bond cannot be broken down, chlorine cannot come out. So the other nucleophile cannot come here and form the bond. Got it? So the first reason is resonance. Second reason is the hybridization. Is it clear? Shall we go for the third reason? Shall we go for the third reason? Students, shall we go for the third reason? The third is the instability of phenyl cation. Suppose we have studied two types of nucleophilic substitution. One is SN1 and the other one is SN2, right? Suppose if SN1 is taking place, it will take place through two steps, right? Because SN1 is a two-step mechanism. So what will happen in the first step of SN1? The formation of carbocation will occur. So if I take this haloarene, okay, and if I form a carbocation, leaving the Cl minus out, I will get a phenyl cation. Phenyl cation means the C6H5 plus phenyl cation. This is a phenyl cation. This phenyl cation is unstable. You know why it is unstable? Benzene is a stable compound, and if there is any charge present on the benzene, it will make the aromatic compound, the more stable benzene compound, as an unstable compound. Okay, so there should not be any charge present on plus charge or minus charge on the benzene ring. It will destabilize the benzene. Got it? Now, since this phenyl cation is unstable in nature, SN1 mechanism is completely ruled out. Nucleophilic substitution can occur at a different condition, but they will occur only through SN2. SN1 cannot be done, okay, because the in the first step, we are getting an unstable carbocation, so SN1 mechanism is completely ruled out. Okay, this is the third reason. And the fourth reason is repulsion. So in all the haloarenes, if you see, all the halogens will have 3 lone pairs. It will have 3 lone pairs. So since they have 3 lone pairs of electrons and also the ring is electron rich in nature, the entire haloarene is an electron rich compound. The entire haloarene is an electron rich compound. And the nucleophile which is trying to substitute, it is also electron rich, right? Nucleophile also has the negative charge and it is also an electron rich compound. Electron rich, electron rich. So the like charges, when they try to approach each other, what they will do? They will repel each other. So repulsion occurs here, and because of this repulsion reason, nucleophilic substitution cannot occur. Cannot occur means it is less reactive. It will occur, but it is less reactive towards this haloarenes. Okay. So what are the 4 reasons which makes the reaction less reactive towards haloarenes? Resonance, hybridization, instability of phenyl cation, and repulsion. And under each case, I have given you the explanations also. So do you have any doubts from these 4 reasons which affects the substitution? Do you have any doubts? Shall we go ahead with the next slide? Shall we go ahead with the next slide, students? Yes or no? Adarsh, Bishan, Madhukar. Every time I have to call your guys' names or what? Jane V. Rowing. Shall we go for the next? Is everything clear up to this? Okay. Thank you so much, Madhukar, for your response. So now we will go for the replacement of halogen by OH. So under nucleophilic substitution, we are going to see this reaction, replacement of halogen by OH. Halogen will be replaced by OH, but not under normal condition, but under different condition. Okay. So the name of the reaction is Dow's process. And here we are going to take a chlorobenzene and we are going to treat it with NaOH at 623 Kelvin and 300 atmospheric pressure and with H+. So I have used a strong base and the temperature is also very high. Pressure is also very high. So under high temperature and high pressure, the Cl nucleophile can be substituted by OH nucleophile. Okay. Cl nucleophile can be substituted by OH nucleophile and it leads to the formation of phenol. Okay. So this is the reaction condition. Reaction condition is very drastic. Drastic means very high temperature and pressure. Only at this particular high temperature and pressure, we can able to substitute the nucleophile on the haloarenes. Okay. Now, I cannot wait for this particular time. No, I cannot wait for so long. I cannot wait for the system to attain the 623 Kelvin and 300 atmospheric pressure. I want to form the product. I want to get the product immediately. So what are the other ways that I can do here on this chlorobenzene to get the product easily and fastly? So there is one way, and that way is introducing an electron withdrawing group on the ring. Electron withdrawing group on the ring. Okay, so here I have introduced the NO2 group, nitro group, which is an electron withdrawing group. I have introduced this in the para position. Para means opposite position to the Cl. Okay, so if I introduce this NO2, if I attach this NO2 group, which is an electron withdrawing group, it will withdraw the electron from the benzene ring. And it makes this benzene ring electron deficient. It makes the benzene ring electron deficient. Okay, so it becomes an electron deficient kind of compound. So instead of waiting for 623 Kelvin, at 443 Kelvin itself, the Cl can be replaced by OH, leading to the formation of 4-nitrophenol. Leading to the formation of 4-nitrophenol. Okay. Suppose I don't want to wait for even 443. I want the product immediately. What I can do? I can introduce two electron withdrawing groups. One at ortho position and the other one at para position. Ortho means adjacent to chlorine. Para means opposite to chlorine. If I introduce two electron withdrawing groups, those two will withdraw the electron side by side. So the electron deficient character will be more compared to the previous reaction. So you see the temperature, instead of 443, we will get the product at 368 Kelvin itself. We will get the product at 368 Kelvin itself. So 1, 2, 3 and 4. So 2, 4 dinitrophenol I am getting. Okay. If you try to introduce one more NO2, 3 NO2, and this is a 2,4,6 trinitrochlorobenzene compound. If I use three nitro groups, all the three will pull the electrons towards itself it will withdraw the electron from the benzene ring and it makes the ring more electron deficient. It makes the ring more electron deficient. So you don't have to give so much of heat. Just the warm water itself enough to replace the Cl with OH. Okay, so we get 2,4,6 trinitrophenol. So we have introduced the electron withdrawing group at ortho position and para position. So the presence of an electron withdrawing group at ortho and para position increases the reactivity of haloarenes by withdrawing the electrons. Okay. So if the ring is becoming electron deficient in nature, means the incoming nucleophile OH minus or H2O, which are electron rich in nature, they can come and approach the electron deficient compound more easily and the reaction will occur very fast. Okay, leading to the formation of product easily. Clear, electron deficient can react with electron rich very fast. So we are making the ring electron deficient by introducing the NO2. This is how we are increasing the reactivity of haloarenes. Is it clear? Can you all able to understand how the Cl is getting replaced by OH? So this is all about the nucleophilic substitution of haloarenes. First of all, it is less reactive due to the 4 reasons. And the substitution is possible at drastic condition. Okay, you should increase the temperature and pressure, or you can introduce some electron withdrawing groups and do the reaction. All right. Shall I go for the second type of reaction, which is electrophilic substitution? Yes. Shall we go for the electrophilic substitution? Do you have any doubts in the first type of reaction, students? Okay. The second is electrophilic substitution. So under this, we are going to learn 5 reactions and all the 5 are very important. The first is halogenation. In halogenation, in all the reactions, you are going to take one of the reactant as chlorobenzene. Okay, because these are the reactions of haloarenes. So I'm taking a chlorobenzene and I'm treating this with Cl2. Halogenation means halogenating agent should be used, right? So Cl2 in presence of anhydrous FeCl3 or AlCl3. So these two are the halogenating agent. So from this halogenating agent, the electrophile generated will be Cl+. Electrophiles are electron deficient compound and electrophiles are positively charged compound. Okay. So we will get Cl+ and that Cl+ will go to the para position and it will go to the ortho position. But para will always be the major product and ortho will be the minor product. Okay. So 1,4-dichlorobenzene is the major product. So this is all about halogenation. So you need to study the halogenating agent and the electrophile that is being generated from that halogenating agent. That's all. The second thing is you have to substitute in ortho and para. Very easy. Okay. So let me go for the second reaction and it is called as nitration. In nitration reaction, I have to use nitrating mixture. It is concentrated HNO3 and concentrated H2SO4. So from this nitrating mixture, I will get NO2 plus electrophile. Nitrating mixture will produce NO2 plus as an electrophile. And that will go to the ortho position and the para position. So it is 1-chloro-2-nitrobenzene and here it is 1-chloro-4-nitrobenzene. So ortho will be the minor and para will be the major. Okay. So please learn the nitrating mixture and the electrophile that is getting generated from that mixture. All right. I will go for the third reaction, which is sulfonation. So in case of sulfonation, chlorobenzene is treated with concentrated H2SO4. Concentrated sulfuric acid on heating is the sulfonating agent. And from this electrophilic reagent, we will get SO3H plus as an electrophile. Electrophile is SO3H plus. And that SO3H plus will go to ortho and para. Okay. So this compound is called as benzene sulfonic acid. And this is taken as 1 and this is taken as 2. So at the second carbon, I have chloro. So it is 2-chloro-benzene sulfonic acid. And here it is 4-chloro-benzene sulfonic acid. Okay. Ortho is minor and para is major. Who is the electrophile? SO3H plus is the electrophile. This is the third reaction. Then the fourth reaction is Friedel-Crafts alkylation reaction. So here you have to take the chlorobenzene and treat it with the Friedel-Crafts reagent. So who is the Friedel-Crafts alkylating reagent? So it will be CH3Cl and anhydrous AlCl3. CH3Cl. This is the alkyl part, alkyl halide. So CH3Cl is treated with anhydrous AlCl3. So from this alkylating agent, the electrophile that is being generated will be CH3 plus. CH3 plus. So if I have some other alkyl halide, if I have C2H5Cl, then the electrophile will be C2H5 plus. Got it? So whatever the alkyl group we are taking, so that will form as a electrophile. So that will go and get substituted in the ortho and para position. So we will get an ortho product like this and a para product like this. Ortho minor and para major. Clear? Shall I go for the fifth reaction, which is Friedel-Crafts acylation? So in Friedel-Crafts acylation, there is only one difference between Friedel-Crafts alkylation and acylation. Okay. In alkylation, we will use an alkyl halide. In acylation, we will use acyl halide. So you see, CH3CO, CH3C double bond O. This is called as an acyl group. This is called as an acyl group. So from this acylating mixture, we will get the CH3CO plus as an electrophile. Okay. So that CH3CO plus will go to ortho and para. Ortho minor, para major. 2-chloroacetophenone. 2-chloroacetophenone means this part is acetophenone. C6H5, COCH3 is acetophenone and chlorine is adjacent to it, right? So 2-chloro and here it is 1, 2, 3 and 4. 4-chloroacetophenone. Clear for all? So these are the 5 types of electrophilic substitution reaction. Okay, let me summarize. In the halogenation reaction, who is the halogenating mixture? Cl2 and anhydrous FeCl3. And from this, we have got Cl plus as an electrophile. And in case of nitration, we have used concentrated HNO3 and concentrated H2SO4. And the electrophile generated is NO2 plus. Okay. Then the third is sulfonation. And here the sulfonating mixture is concentrated H2SO4 with heating. You have to heat this. So here we will get SO3H plus as an electrophile. And in case of Friedel-Crafts alkylation, we will use some alkyl halide, RX, in presence of anhydrous AlCl3. So here the R which we are taking will act as an electrophile. And in case of Friedel-Crafts acylation, we will use RCOCl plus anhydrous AlCl3 and here RCO will act as an electrophile. Got it? So learned the type of reaction and the mixture, the electrophilic substitution reagent mixture, and the electrophile that is getting generated. So these are the very, very important points you have to keep in mind. So this 5 types of electrophilic substitution will follow you in all the organic chemistry lessons. Okay, so we have alcohols lesson, and we will study about aldehydes. We have carboxylic acids, okay, ketones, amines. So this 5 type will follow you in all the remaining organic chemistry lessons. Okay, so in all the lessons, only the reactant will change. So here we are talking about haloarene. So that's why the reactant is haloarene, chlorobenzene. If I talk about phenol, then I will use OH here. Instead of Cl, I will use OH. If I'm going for aldehyde lesson, so instead of this OH, I will have CHO. If I'm going for carboxylic acid lesson, then here I will have COOH, okay, benzoic acid. So only the reactant will change. The reagents, electrophilic reagents and the electrophile will not change. So please learn the reagents and the electrophile thoroughly. Okay? Clear for all of you? Shall we go for the third type of reaction? Shall we go for the third type of reaction? The third type of reaction is reaction with metals. So here I have said we are going to learn 2 reactions. The first is Woods-Fittig reaction. Woods-Fittig reaction means I have to take 1 molecule of aryl halide or haloarene, and it has to be treated with sodium. And the second molecule will be alkyl halide. One is aryl halide and the other one is alkyl halide. And in presence of dry ether, the 2NaX will get removed and we will get alkyl benzene as a product and 2NaX as a byproduct. I will give you an example. So I have taken chlorobenzene and 2 sodium and CH3Cl, chloromethane. In presence of dry ether, I have to remove the 2NaCl and I have to connect the 2 part, the phenyl part and the CH3 part, so that I will get a toluene compound. If CH3 is present on the ring, it is called as toluene. It is toluene. Okay, this is actually wrong. It is toluene. Got it? This is about the Woods-Fittig reaction. Then the second reaction is Fittig reaction. Here I have to take 2 molecules of aryl halide itself. 2 chlorobenzene I will take. Okay, in presence of sodium metal. 2 aryl halide I have to take. Same in presence of dry ether. And 2NaX has to be removed and it will form diphenyl plus 2NaX. Okay. So if I take 2 chlorobenzene, I will remove 2NaCl and I will get diphenyl as the major product. All right. So this is all about the reactions of haloarenes. Okay. So the last reaction, the last topic of this lesson is polyhalogen compounds. So I hope all the 3 reactions of haloarenes is clear to all of you. Do you have any doubts from nucleophilic, electrophilic substitution and reactions of metal, students? Shall we go ahead with the polyhalogen compounds? Shall we go ahead with the polyhalogen compounds? So we have completed all the reaction parts. Okay, all the chemical reactions has got over. All the preparations also got over. So this is the very last topic where we will enjoy and study the uses of polyhalogen compounds. Okay. So shall we go ahead? Bishan and Madhukar. Shall we go ahead? Any doubt? Yes. So what is meant by a polyhalogen compound? Carbon compound containing more than one halogen atom are called as polyhalogen compound. Okay, more than one halogen atom containing carbon compounds. Examples are dichloromethane, in which there are two chlorine, and trichloromethane, in which we have 3 chlorine, and tetrachloromethane, in which we have 4 chlorine. So in all the 3 cases, we have more than one chlorine. So these are some of the examples of polyhalogen compounds. So let us study one by one. So let me take dichloromethane first. First of all, I will show you the structure. Structure is CH2Cl2, which is tetrahedral in structure. And it is also called as, the common name of dichloromethane is methylene chloride. The common name of dichloromethane is methylene chloride. Okay. It is CH2Cl2. This is the formula. So what are the uses of dichloromethane? They are used as a propellant in aerosol. Okay. So it is used as a propellant in aerosols, and also it is used in the paint remover. Okay. So not only these two, it is also used as a solvent in the manufacture of all the medicines, in the drugs. Okay. It is used as a solvent. Dichloromethane is a liquid. So it is used as a solvent, and also for cleaning some metals. Okay. As a metal cleaning and finishing, finishing solvent, it is used. To clean some metal, to polish some metal, dichloromethane is used. Got it? So even though they have some uses like this, it also has more number of health risk also. Health risk means the disadvantages. So when you get exposed to this methylene chloride in air, methylene chloride is nothing but dichloromethane, okay? When you get exposed to this can cause, a person can cause, it cause impaired hearing and vision. It will damage the ear and eye, okay? And it causes dizziness and nausea, vomiting kind of sensation you will get if you get exposed to this. And tingling and numbness in fingers. Tingling means some kind of prickling kind of feeling, okay, in your fingers. Prickling kind of feelings in your fingers and toes. And these are all the 4 disadvantages, the health risk when you get exposed to this. Okay, getting exposed means if you inhale or if you go near to dichloromethane kind of thing. But the direct contact with the skin and eyes, if it falls on your skin or if it falls on your eyes, then it will cause intense burning. See, this is a leg of a person. It has the capacity to burn the skin, and some mild redness of the skin will be there, and it will burn the cornea. You see the eye here, it will burn the cornea also. Okay, so you will lose your vision. You cannot able to see when this compound fell on your eye. Okay, so it has some major disadvantages also. This is all about dichloromethane. Then the second one is trichloromethane. Trichloro means I have CHCl3. CHCl3. This is a trichloromethane, and the common name is chloroform. Common name is chloroform. Okay. So this is a chloroform. It is actually colorless. It is looking like a brownish kind of thing, but it is actually colorless in nature. And it is volatile. Volatile means if you open the container, it will try to get evaporated. Okay. And it is sweet smelling compound, and it is a dense liquid. You can able to see the denseness, right? So you see here, it is a dense liquid. It is not a clear liquid. It is a dense liquid. And it is used as a solvent for fats, alkaloids, and iodine. Okay. Not only these 3 uses, it is also used in the production of the Freon refrigerant R22. It is used as a refrigerant also. Okay. And it is the very important uses anesthetic. It is used in the anesthetic purpose in surgery. This is a very important use. The use of chloroform is anesthetic in surgery. Nowadays, chloroform is replaced by ether because chloroform is toxic. Okay, toxic means it is poisonous. So, nowadays it is the trichloromethane. Chloroform is replaced by the less toxic ether molecule. So, in olden days, the chloroform was used for the anesthesia purpose in surgery. Since it is more toxic in nature, nowadays ether is being used. Okay, these are the uses of chloroform. Now, coming to the health risk of this chloroform, it depresses the central nervous system. It depresses the central nervous system and it also causes dizziness, fatigue, headache, and it damages your liver and kidney. Okay, it causes damage to liver and kidneys. And if you get exposed to this chloroform in presence of sunlight, it produces a gas called phosgene. I will show you the reaction. CHCl3 is chloroform. In the atmosphere, we have oxygen, right? So O2 will react with it. And in presence of light, it will produce COCl2 and HCl. COCl2 is called as carbonyl chloride. And the other name for this compound is phosgene. This phosgene is a gas. Okay. If you keep this chloroform in presence of light, it will absorb the atmospheric oxygen and also the light and it will produce a phosgene gas, which is a poisonous gas. Okay. So that's why to keep this away from the light, they will store this chloroform in a, a dark colored bottle. They will store this in a closed dark colored bottle. Why they are keeping it in a closed bottle, closed container? So that to avoid the oxygen. Okay, if you keep it closed, oxygen cannot come and react. And if you keep it inside a dark bottle, the light cannot come inside the container. So that the poisonous gas, phosgene, cannot form. Okay, so this is a very important reaction. The formula for phosgene is COCl2. This is about the chloroform. And the next compound is triiodomethane. Triiodomethane means CHI3. Okay. So it is called as iodoform. CHCl3 means chloroform. CHI3 means it is iodoform. So earlier it was used as an antiseptic. Chloroform was used as an anesthetic and iodoform is used as an antiseptic. Okay, have a note of it. Very important. And but this has some objectionable smell. Okay, it has some objectionable smell which cannot bear. So that's why this triiodomethane have been replaced by other formulations of iodine. So they have derived some other formulations of iodine and those compounds are used as an antiseptic because of its smell. Okay, so that's all about this. Then the fourth compound is tetrachloromethane. So CCl4, tetrachloromethane. And the common name of this is carbon tetrachloride. Carbon tetrachloride. Okay. And it is used in the manufacture of refrigerant and for the manufacture of propellant for aerosol can. Okay. And also it is used as a feedstock. Okay. As a starting material in the synthesis of many compounds like chlorofluorocarbon and other chemicals. Okay. So you see here. Trichlorofluoromethane. Okay. And difluoromethane. So to prepare the chlorofluorocarbons, carbon compounds like this, it is used as a starting material. Okay, feedstock. And some more uses of this carbon tetrachloride is, it is used as a cleaning fluid. Okay, one of the component in cleaning fluid and in the degreasing agents and the fire extinguisher. So these are the uses of the CCl4. And this CCl4 also has some health risk. Okay, the advantages will be very less only. Disadvantages, I mean the health risk only is more for this type of polyhalogen compounds. So first of all, the common effects are dizziness, lightheadedness, nausea, vomiting, damage to nerve cell. Okay, these are all the common symptoms for experienced by a person if he or she is exposed to tetrachloromethane, CCl4. Okay, but in severe cases, if a person is exposed to this compound in severe case, it will lead to unconsciousness and a person will go to coma stage itself. Okay, and finally it leads to death also. In severe case, it leads to death also. Okay, so you should be very careful with CCl4. Got it? And not only these things, it will deplete the ozone layer. It will deplete the ozone layer. How? It has exposure to UV rays, and if the UV rays are getting exposed, it will decrease the immunity of a person, and all type of eye problem will come, eye disorders will come, and if the rays directly falls on the skin, we will get skin cancer. Okay, so it depletes the ozone layer and it gives this type of health risk for a person. Got it? So these are all the disadvantages of health risk from this CCl4 compound. Okay, so now let me go for the next compound, the fifth compound, which is called as freons. Chlorofluorocarbon compounds of methane and ethane are known as freons. Chlorofluorocarbon. Chlorofluorocarbon CFC compounds of methane and ethane are known as freons. I will give you some examples, you see. So here I have 2 chlorine, 2 fluorine and 1 carbon. Okay. So this is called as freon 12. So chlorofluorocarbon. This compound is prepared from tetrachloromethane only by Schwarz reaction. Tetrachloromethane means from CCl4 only. I have told, right, the previous case. So from CCl4 only, we are replacing the 2 chlorine out of this 4 by the 2 fluorine and getting this using Schwarz reaction. Schwarz reaction, I already explained you in the beginning of this lesson itself. In the halogen exchange reaction, we have studied this. Okay, so this is actually called as freons. And some of the properties of this freons are, they are extremely stable, unreactive, non-toxic, non-corrosive and liquefiable gas. It is having less toxicity. It is not that much poisonous and it won't react with other compound also. Okay, these are some of the properties of the freons. And the uses of freons are, they are used in the aerosol propellant and in the refrigeration and in AC. So everywhere in fridge, AC, everywhere we have this freon. So let us study the effect of this freon on the environment. Okay. So freon will go to, from AC and fridge and all, it will go to the stratosphere. So in the stratosphere area, the freons will produce the free radicals. So what is the nature of free radical? Radical means it is not good actually. Okay. So the radicals will go and deplete the ozone layer. So all of us should reduce the usage of AC and fridge. Okay, because the gas which is coming out of it will produce the free radical and it will deplete the ozone layer. So please try to reduce the usage of fridge and AC. Got it? Now coming to the 6th compound, which is DDT. DDT structure is this. This is DDT and the full form of DDT is dichloro, diphenyl, trichloroethane. Dichloro, diphenyl, trichloroethane. DDT. Okay, so dichloro and diphenyl, trichloro, and here we have 2 carbon, right? Ethane. Got it? So this compound was formed or proposed by Paul Muller. He only discovered the effectiveness of this DDT as an insecticide. Okay, so it has some uses also, right? It is effective against mosquito, malaria, lice, and typhus. So he only discovered the effectiveness of DDT against the as an insecticide. Okay. So even though it has some uses, it also has some health risk. So let us discuss the health risk. So this insects develop resistance to DDT. Okay. Insects will develop the resistance to DDT. Once it starts consuming it large amount, it starts developing the resistance. And also it is highly toxic towards the fish. Highly toxic towards the fish means it is very poisonous to fish. So as we human, we take fish, right? So the DDT which has been taken by the fish is stored inside the fish, and if we are taking the fish, it will come and get stored inside the body, in the fatty tissue of the body. Okay. And the metabolism takes place very slowly. So it is stored as in the fatty tissue of the body, and it is metabolized very slowly, and it acts as a toxic substances kind of thing. Okay, so this is one of the health risk from DDT. So that's because of these reasons, the use of DDT is banned in United States, but still it is used in other parts of the world like India. Okay, so the use of DDT is banned in United States, but still it is used in some other parts of the world also, still today. Got it? So this is the sixth polyhalogen compound, and I hope all the 6 polyhalogen compounds uses and health risk are clear to all of you. So let me summarize the today's topic. So today we have started with the Dawes process, which is the nucleophilic substitution reaction, right? Under drastic condition, we have substituted the nucleophile. And coming to the electrophilic substitution, we have studied 5 reactions. Halogenation is the first one, and nitration is the second reaction. Sulfonation is the third reaction. Okay. And Friedel-Crafts alkylation is the fourth one, where we used alkyl halide and anhydrous AlCl3. And the last one is Friedel-Crafts acylation. These are the 5 types of electrophilic substitution. And later on, in the third, in the reaction with metal, we have discussed Wurtz-Fittig and Fittig. And finally, end of the lesson has the polyhalogen compounds like dichloromethane, trichloromethane, tetrachloromethane, freons, DDT, and triiodomethane. So we have discussed about the 6 polyhalogen compounds at the end of this lesson. Okay, so with this, the lesson is getting over. In the next session, we will start with the new lesson. Okay, so do you have any doubts from this? Do you have any doubts from haloalkanes and haloarenes lesson? If you do not have any doubt, you can start filling up the feedback form. Okay. You can start filling up the feedback form. Thank you so much, students, for attending the lecture today. So meet you all with the next new lesson in the next class. Okay.